Next topic is ripple factor. What is ripple factor? How do we define it? And what is its significance? First thing, what is ripple? So, if I take a bowl and I fill it with water, and I drop a stone somewhere in the bowl, so you can see ripples forming there. So we can see the ripples forming there. So the ripples are nothing but the waves, or you can call it as disturbance. So these are the disturbances that been caused because you dropped a stone in a calm water. So similarly, what is this ripple factor? How do you define DC signal? So we define DC signal. Say this is DC signal with respect to time. It has some amplitude. Say V1. V1 is the amplitude. It is a DC signal. It is continuous with respect to time. There is no variation in this. It should be constant line, a single line. But you get ripples here. See, I told you while defining the rectifier. So it has two steps. One is conversion of AC to pulsating DC. So this is how your DC is getting. This is the output DC what you are taking. Now this is the DC what you are taking. In this DC you have the ripples. These are the ripples. So the presence of ripples in your in your DC signal, you are having some ripples. This is called ripple factor. This factor, like what is this factor? That is defined by ripple factor. That is amount of AC signal present in DC is called ripple factor. So how do you calculate ripple factor? We represent ripple factor by the term gamma. Gamma is equal to, so amount of AC signal, output RMS current divided by output DC component. So gamma, that is ripple factor, is defined as output RMS value of AC component. So here we will take it as current divided by output DC component or current. If I am taking as current, I will take the component as current. So gamma is equal to output RMS value of the current to output DC value of the current. That is defined as IAC divided by IDC. That is defined as IAC divided by IDC. So this is the definition of ripple factor. The presence of AC component. This is the AC component, right? So this is the AC component. The varying component is always AC component. The presence of varying component, that is AC component, in the DC signal, is called ripple factor, is defined as ripple factor. Now I told you that ripple factor is defined as IAC by IDC, right? So now we don't have any direct relation here. So to calculate the ripple factor, what do I do is I take the RMS value, IRMS square is equal to, that is RMS value, that is a mean value, RMS, root mean square value. This value, that is IRMS square of this IRMS value is the component of IDC square and also IAC square. So we take this expression directly. So IRMS square is equal to IDC square plus IAC square. So while calculating the root mean, we will be having, or we include both AC and DC components here. So I need AC. So I'll write IAC square is equal to IRMS square minus IDC. IRMS square divided by minus IDC. So you have square here. Let me put the square the other ways. IAC is equal to square root of IRMS square minus IDC. We know that gamma, that is ripple factor, is equal to IAC divided by IDC. That is nothing but square root of IRMS square minus IDC square divided by IDC. What is the value of IRMS? IRMS is equal to IM by 2. And what is the value of IDC, which is equal to IM divided by pi. So if I take squares, it becomes IRMS square is equal to Im square divided by 2, and IDC square is equal to Im square divided by pi. So substituting this and this in the above equation, I get it as gamma is equal to Im square divided by 2 into 2 is 4 minus, here also will be having square, IDC square, sorry, Im square divided by pi square divided by IDC is again Im by pi. The whole thing under the numerator under root. So the next step, I'll take Im common here. It becomes Im square into 1 by 4 minus 1 by pi square divided by Im by pi, the numerator under root. So I'm taking Im square under root, it becomes Im. I write it here, into 1 by 4 is 0.25 minus 1 by pi square divided by pi. So Im and Im get cancelled. So if you calculate this value, you will get it approximately, not approximately, you will get it as 1.21. 1.21. That is, the ripple factor is 1.21. What is the meaning if I say the ripple factor is 1.21? It means that we can say that there is more than 100%, that is 121% of AC in the given DC component. In the given DC component. In the DC component, you have 121% of AC. That is the significance of ripple factor. The next is rectification efficiency. What is the efficiency of this half wave rectifier and how is the efficiency defined? Now, efficiency is represented by eta. It is defined as the ratio of output DC power delivered to AC input power. It is nothing but, so if I have a box or black box, that is, I don't know what inside it is. So I give some input, I'll take some output. So how much data or how much amount of input I am giving, what is the amount of output I am getting? So what is the amount of input I am giving, what is the amount of output I am getting? So that declares or that will define what is the efficiency. So now what is the output I need to get? Output I need to get from this black box is always DC. What is the input I am giving? The input I am giving is always AC. I am giving AC input to get DC output. So what is the amount? If I give 100 units of AC, how many units of DC I am getting? So that will be defined as efficiency. So DC power is the measuring unit. So DC power is the measuring unit here and AC power is the measuring unit here. So what is the amount or what is the power of DC I am getting and what is the power of AC I am giving into it? So that will define the efficiency. So we call it as PDC, power DC, which is obtained at the output, and power AC, which we have given at the input. This is the ratio that defines the efficiency. Okay, so now PDC, that is power of DC output or DC output power, is given as DC square into RL. I am taking current because I have calculated the values of current in previous stages. So current IDC into RL, and PAC is equal to IRMS square into RF plus RL. So what is this RF and RL? RF is the forward resistance of diode. RL is load resistance. Forward resistance of diode. You have the diode. When you write the piecewise linear model, you write resistance, you write voltage source and then the diode, right? So this is RF. And RL is the load resistance. If you just remember the circuit of the rectifier, you have RL here, right? So this is the value of RL. So this RL, I am taking it here, RL. Okay. So the next step is I have to substitute in terms of efficiency. Efficiency is equal to IDC square into RL divided by IRMS square into RF plus RL. So how did I write P is equal to I square into R? Simple equation. We know that P is equal to power is equal to current into voltage. Now we don't know voltage because we have calculated all in terms of currents. Therefore P is equal to I into V is equal to I into R. That becomes P is equal to I square R. Okay, so this is how I have taken this. P is equal to I square into R. Here PAC is I square into R. R is the resistance. Now efficiency. We know that IDC is equal to IM divided by pi. Therefore IDC square is equal to IM square divided by pi square. And IRMS is equal to IM divided by 2. So it IRMS square is equal to IM square divided by 4. Substituting it, so we get efficiency is equal to IDC square IM square divided by pi square into RL divided by IM square divided by 4 into RF plus RL. So we have efficiency is equal to IM square. I am rewriting the expression pi square into RL divided by IM square divided by 4 into RF plus RL. Now, so IM square I can directly eliminate it. So I have the parameter now 4 divided by pi square. Denominator of denominator will become numerator. So 4 divided by pi square into RL divided by RF plus RL. Okay. So 4 divided by pi square, the value will be equal to, if you use calculator, you will get it as 0.406. 406 into RL divided by RF plus RL. Suppose, this is the efficiency. Suppose RF value is very much smaller than RL. That is, RF normally it will be very less, whereas load we actually take in terms of mega ohms. So therefore, the RL value is very high compared to RF. If RF is very much less than RL, say for example, I assume that, it is just an assumption, the value of RF is 10 ohm and RL is 1 mega ohm. So if I assume that RF is just 10 ohm and RL is 1 mega ohm, so RF is 10, 1 mega is 1, 1, 2, 3, 1, 2, 3, 1 mega. So if I add it, it becomes 1, 1, 1, 0, 0, 0, 0, 1, 0. So it is again approximately equal to 1 mega only. That is why I take RF plus RL is equal to RL. So RL is 1 mega. Therefore, the result is also approximately equal to 1 mega. That is why I take RF plus RL is equal to RL. Then what happens to the equation of efficiency? Efficiency is 0.406 into RL divided by this complete term becomes RL into RL into RL. So RL and RL get cancelled. Efficiency is 0.406. Or if I tell the same thing in terms of percentage efficiency is equal to 40.6. Percentage efficiency is 40.6. That is nothing but when I want to use or when I am using a half wave rectifier, the efficiency of half wave rectifier is just 40%. If I send 100 units of AC power, I will be getting only 40 units of DC power at the output. So this is the efficiency and the significance of half wave rectifier. The next heading is peak inverse voltage. What is peak inverse voltage and what is its importance? First is definition. It is the maximum voltage that appears across the diode during non-conducting condition. Non-conducting condition is the reverse bias. So when your diode is not conducting, so this is the diode. When it is not conducting, it behaves as an open circuit. What is the maximum applied voltage or what is the maximum voltage that we can apply? We can apply across the diode is called peak inverse voltage. Suppose it ranges as 10 volts. it is given as 10 volts. So this will be PIV value will be specified by the manufacturer. So they'll give the rating, like what is the maximum voltage you can apply. See, if they say as 10 volts, whatever the applied voltage is there, you apply, what we apply, it should be less than 10 volts. If you apply more than 10 volts, the diode will break down. That is, it damages the diode. It damages the diode. So this PIV rating shows that what is the amount of voltage that we can apply to the diode in reverse biased condition. This is about peak inverse voltage. Next is advantages. What are the advantages? What are the disadvantages of this half wave rectifier? Now in half wave rectifier, what is the advantage? It has only one diode. It is very simple circuit, and it is very easy to analyze also. Coming to the disadvantage, the ripple factor is 121%. It is not just, or it is not equal to 100. It is more than 100. That is, whatever the amount of DC you require, more than the DC you have AC component in that. So AC component is more than the DC component. So that is what ripple factor tells. So this is one of the major disadvantage. And coming to the efficiency, it is just 40.6. Percentage efficiency is 40.6. That is not even 50% efficient it is. It is less than 50%. Efficiency is very less. So with this sort of efficiency, you can't achieve anything. Therefore, this is one of the drawbacks. These are the two major disadvantages that half wave rectifier has. The only advantage it has is it has only one diode. The circuit is simple. That's all. So this is about half wave rectifier. The process of rectification can be divided into two parts. The first one is rectifier. The next one is filter. What is rectifier? So we have seen till now, that is half wave rectifier, or full wave rectifier, or bridge rectifier. So these are the three different types of rectifiers that we can accommodate in this rectifier block. The next one is filter. So there are different types of filter. Here we will concentrate on only one type of filter, that is RC filter. So what is the difference? Like what happens when we go for rectification is, I'll give an AC signal. This AC signal is converted to pulsating DC. It will not be converted to DC. It will be converted to pulsating DC, and later it will be converted to DC. So if this is their AC signal, so it will be converted to pulsating DC. This is half wave output. I am writing half wave rectifier output. You have pulsating DC. This pulsating DC you can't apply, or we can't use this pulsating DC to anything. So what we have to do, we have to convert this to actual DC. How do we convert? Like we will give it to the filter circuits. So filter converts the pulsating DC to actual DC. It converts the pulsating DC to DC. So this is the process of rectification. Rectifier just converts the AC to pulsating DC, not to the complete DC. And the filter will convert the pulsating DC to DC. Now let us understand what is this filter circuit. So this is the rectifier circuit with the capacitor. Now this part C and RL is called the filter. Now this is the output. So the dotted lines what I have shown here. So this is the output of your half wave rectifier. This is the output of the half wave rectifier. Next, what I am going to do is, because I have a capacitor here, what happens to the signal here? The diode will allow the positive pulse and it will block the negative pulse. So we don't need to bother about the negative pulse. We have positive pulse here. First, the positive pulse will store in the capacitor. It will store across the capacitor. Capacitor is used to store the charges, right? So this positive pulse will be stored here. It will be stored here. How does the storage takes place? I assume that this is the very first pulse. This is the very first pulse. So the capacitor slowly starts charging. It will charge up to the peak point. After the peak point, the input wave or the positive half pulse will discharge. Okay, so it is discharging. In this discharging phase, the capacitor will not lose its charge instantly. It will not lose the charge instantly. It will not fall like this only. It will discharge slowly. It will discharge slowly. That is, it will discharge slowly. Like this it will discharge. So once it is discharging, slowly it is discharging. So by the time it reaches the discharging point, you will be getting another pulse. You will be getting the second pulse. Now this is the first pulse. You will be getting the second pulse. So this is time axis. So now at the second pulse, what the second pulse will do? Again it is having the increasing phase. That is, it will start storing the charges again. So again it will charge back. Once it reaches the peak point, again your second pulse will discharge. Because it is a capacitor, it will not lose its charge immediately. It will discharge slowly. So this is a slow discharge and this is the charging period. Again, while discharging, it will encounter the third pulse. Once it encounters the third pulse, again it will start charging. So after the peak value, again it will start discharging. This process of charging and discharging continues. It will continues. Now coming back, I'll explain you the waveform first. So coming back here, this is the point or maximum voltage point, we call it as Vm, and this is the capacitor discharging, or this shows the discharge of capacitance. And this is your charging of capacitance. So from this point to this point, that is when the discharging line encounters the next peak to the peak point, this period, like when the signal is raising, that is called charging time. And from the charging point to the next peak encounter, from this point to this point, is discharging time. So this is charging time and this is discharging time. So these are the different parameters of your capacitor filter. Now even though if I see the signal, I can see the signal varying like this. This is a first cycle. I'll just assume that I don't have first cycle now, or I lost the first cycle. Then your charging and discharging peaks will be like this. If this is the 0 axis or time axis and this is the 0 line, your charging and discharging values will be like this. If I increase the value of capacitance, this charging and discharging can also be eliminated. That is, if I increase the value of capacitance, this will be the charge, discharge will be almost like this. Or you may get a straight line, which is a DC signal. If I increase the value of capacitance, you will get an absolute DC signal. This is how you convert an AC signal to pulsating DC and then to DC. Okay, so this is the process of filtering. Why do we need this filtering? We need this filter to reduce the ripple factor. So as I mentioned in the previous class, the ripple factor of half-wave rectifier is 121%. Right? To reduce this, we use this. So ripple factor is again defined as VAC by VDC, and it is given. You have direct expression for this. You don't need to find the expression, like no derivation for you. You have to just remember this. So gamma is equal to 1 divided by 2 into root 3 FC into RL, where F is the frequency and C is the capacitance. What we have used. RL is the load resistance. So using this formula, you can find the ripple factor. So here the ripple factor for a perfect DC will be less than 0. It will be less than 0. You won't get any ripple factor at all. So this is all about half wave rectifier.